stationary phase methods, a new class of stationary phase methods, I guess.
It's the nonlinear one.
Nonlinear.
Thank you. Yeah, I'm very grateful for the opportunity to speak here, and thank you for attending my talk. Today I'll be talking about a nonlinear analog of the classical stationary phase method that is useful to study decay estimate and asymptotic of solution to a large class of nonlinear equations. So I will start with some background from linear theory. One fundamental tool in linear theory is the Fourier transform, and that's the formula. Oh, sorry. Okay, and it has many symmetries. And one particular property is it has the ability to convert spatial derivatives into frequency multiplication. And this is why it's really useful for solving linear equations. Okay, and you can take the Fourier transform of a linear ODE, and then you can solve it by separation of variable. And if you solve, like, I don't know, 5 linear equations, you sort of realize certain patterns. If you let some initial data evolves using a linear equation, then its Fourier transform evolve by multiplication with some oscillatory function. So there's some oscillatory factor here, and this is the Fourier transform of the initial data. Okay, and the phase here certainly depend on the algebraic structure of the equation. For instance, if you talk about the Schrodinger equation, you can say it's minus c squared. Okay, so it's very standard. So in other words, you see, if you ignore everything, you just look at the dependence on t, then the Fourier transform linearize the evolution. Basically, t becomes t times theta. So it linearized the whole equation here. Okay, so so we know how to solve our linear equation in the frequency sign, and we can recover the original solution by taking the inverse Fourier transform. And at the end of the day, we get some integration of some oscillatory integrals. And here we have two things. First, the phase theta c here comes from the evolution of the frequency, and this factor is come out of the inverse Fourier transform. So we can think about like this phase has encoded the variable x, and then we just have some oscillatory integral. Okay, and oscillatory integrals appears in many other settings, and as much as we like to understand, we want to know the asymptotic of our linear solution or decay estimates and things like that. And classically, there are two fundamental methods, the steepest descent method and the stationary phase method, and I will briefly talk about them before going to nonlinear theory. Okay. So the main idea of the steepest descent method is deformation of integration contour. So we have some integration along the real line, and we just deform it. And we can do that via Cauchy theorem, and assuming you need certain analyticity here, but okay, let's just assume we have that. So it's just a deformation of contour. And the whole point is we like to have a, in the limit as t go to infinity, on the contour here, except for some endpoints, you have some convergence. And in this sense, you have some decay of the oscillatory term here. So deformation converts this oscillatory term into some sort of exponential decay. And one thing we have to be careful is we don't have that much freedom to deform the contour. Okay, we have to be careful with the direction of deformation. Okay, so if we look at the picture carefully, if locally the derivative of the phase is increasing, then we have to deform it to the upper half plane. And if the phase is decreasing, then we have to deform it to the lower half plane. And why is that? So essentially, we want to have a positive imaginary part here. Right? That's the reason. And you see on the real line, the imaginary part is 0. So it just follows from Cauchy-Riemann equation. Okay, so the fact that the derivative here is positive tells you that the imaginary part will be increasing slightly. So that's the reason. Okay, so you don't have that much freedom, but you have to understand the signature of theta prime. And as a consequence, you see that the endpoint of gamma here are exactly the places where the derivative is equal to 0. And that's called the stationary points. And so as t go to infinity, this integral is going to localize at this endpoint, and you can extract asymptotic, and so on. So the main idea of the classical stationary phase method, which is the sort of historically more popular, is to exploit the oscillation of this oscillatory factor. And this is a sketch of this function. And let's just look at the picture carefully. Okay, so like near some point C, I can approximate my phase using Taylor approximation. Okay, and then so this guy is just a constant locally, and the theta prime here is going to be encoded in this frequency. So basically, locally, it oscillates with this much frequency. Okay, so if theta prime is non-zero, you out here, and t go to infinity, this guy oscillates faster and faster. And once you integrate like this sort of graph of a function, you expect a lot of cancellation, right? So away from the stationary point, you see a lot of cancellation. So that's the effect of t going to infinity. On the other hand, if C get close to the stationary points, it's sort of negating this effect. So somehow you have to compromise and get a correct cutoff region. And doing so, you can get the leading asymptotic. Okay, and we can see that the width of this cutoff region tell you a little bit of the decay. And the size of this cutoff region depends on the order of the stationary points. And high order basically mean the graph is basically fatter. So a point has order k if the first k derivatives is equal to 0. And you can see with higher order, it becomes fatter, and the derivative becomes small for a wider interval, and you get weaker decay. Okay. So this is a very classical theorem, and you can look it up in books like Stein. And so the theorem essentially say, if you don't have any stationary points, then you can get arbitrary decay, given enough regularity in decay. So you can get as much as you want. Okay.
As long as G is smooth, right?
Yeah, G is smooth. We have the regularity and decay. Okay, I just ignore that. But if you have a finite number of stationary points, then you can extract, so the asymptotic of your integration is the sum of contribution coming from these stationary points, and for each point you have 1, and this is the higher order term. And we can see that the higher the order of alpha e, the weaker the decay is. It's consistent with the observation. And you can compute exactly what this magnitude is. Okay, so there's a t here, but it doesn't affect the magnitude. It's just some unimodular term. Okay, so you can sharp asymptotic, get sharp asymptotic by either method. So I like to point out 2 things. So if we are only interested in the overall decay estimate, then it's good enough to use real variable methods like integration by part, or a slightly more fancy version is van der Koppel's lemma. Okay, so you don't need to use complex method. But if you want to get sharp asymptotic, at some point you have to use steepest descent. And the whole idea is we have to first of all localize this integral to the situation when you have only 1 stationary points by using localization and linearity. And then near each stationary point, we perform a phase reduction, and then everything becomes nice, and then you can use steepest descent to get the leading asymptotic. So again, if we only interested in the overall decay, then it's good enough to use real variable tools. But for sharp asymptotic, you need the full strength.
Sorry, when you say sharp asymptotics, I mean,
yeah, you can get exactly the leading asymptotic. You know exactly what it is.
I mean the coefficients then.
Yeah. So you know exactly what's the leading asymptotic, and
I mean, the power of t, it's, I mean, you can get it just by...
Right, yeah, but
it's just the coefficient basically
yeah.
to control it. Okay.
Correct, yeah. Okay. So, so these are linear theory, okay? They're very classical, and I guess people got bored at the moment. So what we will talk about in the next couple of minutes is a nonlinear analog of this method for nonlinear equations. So the Fourier transform basically is very useful for understanding linear equations. And there are nonlinear Fourier transform, which is useful in studying nonlinear equations. And one example of that is the scattering transform, which I'm going to define momentarily. It is a nonlinear Fourier transform for a large class of popular equations, such as nonlinear Schrodinger. This is nonlinear Schrodinger, one dimension, mKdV sine Gordon, and a few others. So basically, we have a function f, and how do we define the scattering transform? We basically solve this ODE. So for every fixed frequency, this is an ODE, okay? And we start from some initial data, and then we let the function evolve following this ODE. Okay, so if we look at it carefully, if we ignore these three terms, and we basically look at the linearized version of this ODE, okay? So only that term and the initial data is 1. We essentially recover the Fourier transform, okay? If we linearize it and solve the ODE by, I don't know, separation of variable, the solution will be the exponential of the Fourier transform, okay? So it's so if you linearize scattering transform, you get the Fourier transform. But that's not the most interesting thing about the scattering transform. So the main reason why it is called a nonlinear Fourier transform from say NLS is if we look on the scattering side, we have some nonlinear flow. So we take the scattering transform of our initial data and the scattering transform of the solution at time t. Then the flow in the scattering sign is a linear evolution. Okay, so in other words, you can see GT is the scattering transform of the solution at time t. It's just some sort of conjugation of the initial scattering transform. And here again, if you ignore everything that has C, just look at T, then it's a linear flow. Okay, so in other words, the scattering transform linearize the equation.
So F is the initial condition for the NLS. For
right, so initial data, and you let it flow.
And then you let it flow, and then you look at the G, and
yes.
let it flow, and then you
yeah,
see,
right.
That's linear.
Right, so the evolution on the scattering sign is linear. But you see, we start with a very nonlinear equation here, but you do some hard work here, it becomes linear. Okay.
This is a fairly special
it's a very special transform. Okay, so this transform here, it works for these three equations and a few others. There's KdV and I think some other equation I don't remember, but you probably have to modify this a little bit with some different initial data or certain algebraic changes. But
sorry, how does the nonlinear part of the equation reflects in the nonlinear Fourier transform?
Right. So essentially, if you can think about this as a sort of like a eigenvalue problem. You can think about C here as some sort of eigenvalue, and you can think about this as some sort of spectral equation. Okay. You just think about you can reformulate this one in terms of some eigenvalue problem. And what's interesting is this nonlinear flow doesn't affect the spectrum of the operator, and that's why you see it's a long story. Okay, but
so let me see. Let me make sure I understand, because I used to know these things, but I sort of forgotten them.
yeah.
So you start with an initial condition.
Yes. Let's say this is F.
F.
Yes.
Then you let it.
Let it flow by.
Let it flow by KdV or
Yes.
whatever,
Yes. Yes.
or your nonlinear
Mhm.
you have up there, which is I
Mhm.
guess just as good.
Right.
And then what?
Right, so-
then I solve this equation.
Right. So this equation you can somehow formulate it in terms of some I don't know, L of phi equal to C phi. You can, yes. So L here, that depends on T. So there's some operator, you can reformulate that equation with some change of variable, you can do it. And so L here, okay, it has some, depends on F, okay, but phi here is something like G e to the I mean, some modulation of G. And the fact that the evolution of F here doesn't affect it's going to affect this guy only. It doesn't affect the spectrum of the operator.
Okay, so, yeah, all right.
Yeah, and the only effect that it has on the equation is the boundary value. And once you know exactly what the asymptotic behavior of this eigenfunction, you can show that it only differs by these oscillatory terms. Okay, so in some sense they're comparable with this operator L, these flows. The NLS or mKdV, they're compatible with this flow.
So I have to take the limit as x goes to infinity. I mean, it is a scattering data that flows, right? I have to take the limit.
Yes.
In the previous one, x goes to infinity. That's the G infinity.
Right. Yeah. Okay. So it's a very long story. Okay. It's but roughly that's what it is, and a lot of details I'm hiding here. But if you believe that okay, the scattering transform linearize these equations, then we're happy to go. Okay.
So you take an F, you get a G.
Yes.
That's the G infinity, right?
Right. Yeah, I know infinity. Yes, it's infinity.
Then let that flow under this conjugation, and then the other.
Right.
So, okay.
Yeah. So it's like some sort of commutative diagram in some sense. Yeah. Okay. So then basically we understand the nonlinear Schrodinger very well on the scattering sign, but we like to understand these maps, how to go back and forth. Okay. And so we'll talk about how to recover f of x and t, xt from this scattering data. So let's just talk about recall how we recover the inverted Fourier transform. If we look at this inverse Fourier transform carefully, you can think about f of x as some sort of integration of this modulation of Fourier data. Okay, it's a linear integration with these Fourier data. You just integrate them together. So in the same sense, you can recover the scattering transform by certain nonlinear integration of similar modulation of scattering data, and this is I'm going to talk about later. But this involves some Riemann-Hilbert factorization of some normalization of G. Okay, so all I'm saying here is the way we invert the scattering transform is by doing some similar thing. We don't have a linear integration, but we have some nonlinear integration. And so let's just talk about linear integration from a different perspective. Okay, so if we have a function, we can always decompose it into two components. Okay, this is the Hardy decompositions. Basically, we break it into terms with opposite, with analytic continuation to opposite half planes, and they have some normalization at infinity. Okay, so that's well defined. And how do we can take either components and take an appropriate limit. Then you can recover the integration of J. Okay, so this is just follow from Cauchy integral formula. Okay, if you look at this limit.
So the H plus you can continue in the lower half,
upper half, yes,
yeah,
yes.
The H minus the lower
Yeah,
half.
so it just follow from, I think, 1/2 pi I f. Okay, maybe there is some constant here. But once you send z in, you put z here, basically it cancel out, and you get the integration. Okay, so that's just, so you can integrate your function slightly sort of strangely, but this is exactly how it becomes nonlinear. So the nonlinear analog of a Hardy decomposition is Riemann-Hilbert factorization. So instead of a sum, we have a multiple. Okay, and we have a similar normalization. We have some analytic continuation to upper half plane and lower half planes, and these guys are normalized at infinity properly. And so we can start from a function. We can factorize it in the Riemann-Hilbert sense, and and then we can recover. We can call this thing a nonlinear integration of J. Okay, so if we have a sum here, then we get the usual integration. But here we have a multiple, so we just call it a nonlinear integration just for easy reference. Okay, so
if the matrix is commutative and I took logs, it would be n log.
Right, if it's commutative, it's exactly the same, just exponent, modular some log term. But we are in the matrix setting, it's not commutative, so it's.
So is this decomposition in general? Is this decomposition difficult to do, or is this?
It's difficult. Yeah,
yes,
it's not easy to show existence or uniqueness or even. Right. So a lot of the hard work has to be to show.
In that decomposition.
Yeah, to show the existence, and it's part of the work, but I'm not trying to emphasize on that. It's.
So it's not the same decomposition there with log f rather than f.
Because the matrices don't factor.
The matrix don't factor. You don't have that freedom. Yeah. If you have a scalar, then yeah, essentially it is the same, but then you don't have that freedom here. Okay, so so then if you believe that this is a nonlinear analog of the usual integration, then when we, so I have some diagram here. We have we understand exactly what this guy is. Okay, and then we just do nonlinear integration to recover f of x t. Okay, so if we do that, we get a nonlinear.
You went a little fast.
Sorry, yeah,
sorry.
yeah.
You have a G of t.
Yes,
now
which has.
How are you going to use this decomposition? You want to go backwards, right?
Right, I want to go backward to recover my nonlinear. Yeah. Yes. Okay. And
how do you do that?
Yeah, I will talk about it. Yeah. So you have some.
Are you going to use this factorization?
Yes, I will use. But I'm not going to start from G. I have to do some normalization before I can factorize. Yeah.
But that is not G with x equal to infinity. It's forever.
That's infinity here. Okay, I ignore infinity here. Okay.
But so you want to recover fx of t without knowing G at any x?
You have to do some modulation and normalization. That's what I said.
Yeah,
See, you have to do some modulation.
Limit.
See, if you don't have x here, right, you get f of 0, but you have to modulate. To
You don't send x to infinity.
No, I don't send x to infinity. No, I don't do that.
Well,
Why would I want to do that?
Infinity is the x on the original problem.
So this is like an ODE.
Yeah.
For every fixed frequency, you solve this ODE, you get a function of c. So that's your scattering data. But this guy, you can see it incorporates the whole information about f. It's not just a single point. Okay. It's just like the usual Fourier transform, right? You have to know the whole function in order to define, right? Right. Okay. All right. So if we, so basically, so this is the matrix J. Okay. So it has this form, and P and Q are essentially like ratios of the entries of G. Okay, and this normalization is, I mean, it comes out naturally, but you can think about like in some sense that it has some correct normalization here. I mean, okay. So P and Q here usually if you have a G equal to AB, BA. I mean, I don't know. Usually they have some Lie structure. P is like B over A, and then Q is like B conjugate over A. So these are just ratio of the entries of.
So you get the J from the G.
That's right. Yeah, that's like a normalization of J, and then you have to do some modulation. Okay, so the modulation here, it's just like what we have here. Oh, sorry. Wait, where am I? So we're gonna have to put e to the ixc into P, and e to the minus ixc into Q. Okay, and then we have to incorporate the evolution in time t, which goes back to this phase. Okay, so x is incorporated into this phase, but if you write down, you have x. Okay, so that's just, so you do some modulation and normalization, and then you perform this whole nonlinear integration. You get some nonlinear oscillatory integral. And yeah.
I'm sorry, could you show once again the slide with the inverse transform?
This one, right? Yeah.
So,
So J here is constructed from G. You mean this line, right?
the inverse, just the inverse. You had a slide in the beginning with the.
This one?
With the formula for the transform itself.
Oh, this one?
Yeah. So this is.
So if you linearize it, okay, let's just do some exercise. You have a D of G. You linearize it. you get ei xc f of x, g of xc. Okay, and then you can do whatever, you can do some change of variable here. Okay, you can bring this term and then get a derivative of the log, and then you get log equal to that, and then you get the Fourier transform. This is the Fourier transform. Okay, so it comes out naturally.
In general case, we just what do you mean by reverse transform? Just to solve this to.
Say that again.
Okay, no, I think.
Okay, so different transforms going to solve different equations. Okay, it doesn't solve all the equations, but for these.
This particular one does the sine Gordon. Does the,
sine Gordon.
Does the NLS, right?
Yes, right. KdV you have to do some slight changes, but okay, but.
Sorry, I return to the first question. The nonlinearity. Here it's in particular u squared times u. I don't know if you have u to the power 7 or whatever else.
Then it's not integrable by this transform. Maybe there's some other transform, but not for this transform. Okay.
So there must, at some point you must see the structure of the nonlinearity appearing in this, I don't know,
there's infinitely many equations that are integrable by this transform, but okay, the one that are interesting, okay, are listed here.
Now this transform requires the equation to be completely integrable.
Yeah, that's just an equivalent way of saying it. It's completely integrable. Yeah, but it's not every equation is solvable by this transform. Okay, you don't even know what nonlinearity is doing.
That's special to that particular equation.
Right. For that equation, you can cook up some, but
it's not obvious why that works.
It's not obvious. It's the whole 50 years of literature and so we. Okay. Any questions? I hope we understand this transform because it's going to get a little bit messier.
It's important. It takes a little while to get to it. But
so one thing I can like to say is variants of this transform also appear in other settings, like in the theory of orthogonal polynomial. So if you have a measure, you can define the orthogonal polynomial as scattering data of this underlying measure, and it has very similar structures. And a lot of work in the literature recently is to do one model and the other model. And if you understand the two models well, it's essentially very similar. Okay, but so where I? Okay, so again, this oscillatory type term enter the whole integral via this evolution on the scattering sign. And we would like to understand two things. First of all, decay estimate for our nonlinear equations and nonlinear solutions, and a long-time asymptotic. Okay, so we like to understand that. And it's the same question in linear theory. Decay estimate and long-time asymptotic for the linear solution. And do we have an analog of linear tools like a steepest descent and stationary phase? And the answer is yes. Okay, let's start with some technical detour. If you don't care about soliton, then ignore this slide. So when I define the transform, you see there was a place that was plus and minus. And you see it corresponds to different version of the transform. And if you have a focusing equation, in general you expect to have a solution with some soliton encoded in the solution, and there's standard reduction that allow you to erase these transforms. So we're not going to worry about that. Okay, it's just technical remark. So we're not going to worry about. And these soliton correspond to the poles of the Riemann-Hilbert factorization. So you don't have the two factor it's not entirely analytic, it's just meromorphic. So these poles correspond to the soliton, but we're not going to worry about that. We just ignore that. Okay, that's just a technical detour. You can ignore that. Okay, so first I'd like to talk about the nonlinear steepest descent, which was invented by Percy Dive and Zinzhou in 1993, and they started by studying mKdV and then NLS. So this is exactly a nonlinear analog of the linear steepest descent method. Okay, and in the context of our nonlinear equations, if we do the whole thing, if we have some we have some nonlinear oscillatory integral. So I'm just talking about the result here. I haven't described the method, but at the end of the day, you get some asymptotic, okay, which looks similar to the linear asymptotic. There's a higher order terms, which is encoded in this big O term, and the linear asymptotic is essentially similar. You have a log t here, which is sort of new, and in this magnitude, you can see that it doesn't only depend on alpha; it depends on other stationary points. It is because there's an interaction between stationary points, and that's the nature of the nonlinearity. You can't ignore that. Okay, so I don't have I write a alpha, but it depends on other stationary points. And this log t b here is going to be real value, so it doesn't really affect this decay. Okay, so their method gives this result for mKdV and LOS, and of course the trend is to, I mean their method is some sort of a nonlinear analog of the steepest descent. So it requires certain analyticity, and the trend is toward rougher phases. And like I said, there's a connection to orthogonal polynomial theory where you really need to understand non-analyticity.
You want to be able to do things where what your initial.
So the phase here, yeah, there's some phase here, right? So each integral has like a phase, and you want to be able to do it for like non-analytic phase, okay? And in the setting of PD, it's, well, it depends on what question you're asking, but okay, if for this question, for PD, most of the time you might have a polynomial, so it's okay. You don't have to worry about that.
But for example, in the context of nonlinear Schrodinger,
it will be C square, yeah.
Yes, of course.
So it will be analytic, yes.
Oh, so then you don't have to worry.
You don't have to worry about that, okay. But for the orthogonal polynomial model, you need to worry about that. I mean, even for the PD, if you look at another, it's not long-time asymptotic, but other asymptotic, you might encounter non-analyticity, but it's
where's the I don't understand. Is the non-analyticity in this context? Non-analyticity in the initial data, or is it, where is it? How do I think of this?
So the phase here depends on the algebraic structure of the equation, right? So for NLS, you have a C square, that's theta, okay, plus x over t if you wish, and for mKdV, have a minus CQ plus x over t if you wish. So you treat these things as a constant, okay, and they're polynomials, okay. So
these are phases which are appearing from the classical Fourier transform. Yeah, I mean.
Yes, exactly the same. Yeah, exactly the same as the classical Fourier transform. Yeah. So these things are exactly the same as the classical phase that you get in the linear theory. That's why they sort of magically the same.
So that's what happens essentially if you drop your nonlinearity, right?
Yes, exactly. Yeah. If you use Fourier transform for the linear counterpart, then exactly the same phase. Yes.
Okay. So are you interested in the case where those dispersion relations are not analytic?
So yeah, this is theta. I'm interested in the case when theta is not analytic in C. Okay. So in this, in the long-term asymptotic, you don't have to worry too much about that. Okay. But anyway, the method is entirely different. And for the orthogonal polynomial model, it's much clearer that you need to worry about that issue. Okay, so I'm still good in time. Okay, and so after the work of Dive and Zhou, there has been other extensions. So 3 years after this paper, Vazugin developed some ideas, and he was able to handle very smooth very smooth phases with primary stationary points. So primary stationary points are stationary points of order 1. Okay, and I think his main contribution is the introduction of a localization principle. Okay, so you have some integral, nonlinear or linear, but you want to localize it to one stationary point, and to do that you need to understand some localization. And in linear theory, it's just integration by part. But in nonlinear theory, it is much harder. And I think his main contribution is this principle. And recently, there's some work by McLaughlin and Miller. And they use complex variable method. So instead of using analytic continuation, he used some sort of d-bar continuation. So I don't know. You have a function here, and you like to continue up here. If you have analyticity, then you just continue it. But in some case, you don't have that freedom, so you just set your target here and your original function here, and you solve the d-bar equation with very small error term here. So at the end of the day, you can get something that's sort of imperfect, but you can control the error term. You can do something with it.
Can you get something as sharp as what you get in the analytic case, or not?
Say what?
Can you get estimates that are as good as in the analytic case? I mean, these are
usually when you have a rougher phases, the function you can have probably essentially the same regularity, but you need probably better decay. It's the same as linear theory. Once you have a weak, if the phase is better, you have worse functions. Okay.
So what is the analog of this in the usual steepest?
You can have a linear theory. Yeah, you can exactly do the same thing in linear theory, but in linear theory it wasn't a question because you already have these two powerful methods. I'm not sure if that's your question.
In linear theory, you also have the same problem if you have
Yeah, you use stationary phase, right? That's what you use. Right. That's exactly what a stationary phase method do. When you have a non-analyticity, you use stationary phase.
So you don't do any contour deformation?
No. So this method was yeah. You don't need to do contour deformation for linear theory. Okay. So does it answer the question? Okay.
What was the motivation back in Miller?
They want to do it for better phases, like a rougher, and they try to bring it down as much as possible, and they could do it for two Lipschitz derivatives phases with two Lipschitz derivatives, which.
But these systems with these phases that you're talking about, do they correspond to nonlinear problems, or are you just now abstracting how to do the inverse problem?
Okay, so.
So my question,
okay, okay, I can answer that. Yeah. So let's say let's just talk about the orthogonal polynomial model. Okay.
Then I understand.
In this setting, and you don't have that question. Okay, but the technique for the nonlinear for Riemann-Hilbert is the same thing. So you try it at other models. Yes. But I can relate to another question. There's a zero dispersion limit, okay, in which case the phase depends on the initial data. And if you ask for analyticity, then you're asking the initial data to be analytic. And
so this arises in zero dispersion?
Yeah, it also arises. It's two other questions. Okay.
From the PDE point of view?
Yes, if you just talk about PDE, that's the question, yeah. All right. So I, based on the work of Vazugan, and I was able to handle stationary phase of arbitrary orders, okay, and I can do it for less than two Lipschitz derivatives, okay. So, and the main thing is I only use a real variable method, exactly in the same spirit of a classical stationary phase, okay. And so two things: if you only care about decay estimate, then you don't need complex method. And to get sharp asymptotic, we have to perform a couple of reductions. Do localization and separation of contribution, and then perform phase reduction, and then use steepest descent. So exactly the same spirit of the linear theory.
So in this work that you do in Vazugan's work,
yeah.
Do you use this factorization still? Is there a factorization that you use, or there's no factorization?
The Riemann-Hilbert factorization? Yeah, it's you have to work on that because that's how you define the integration, right? Yeah. But I'll talk more about that. Okay, definitely I'll talk about that. So this is slightly technical. So we know that we have something when we do when we decompose a function into Hardy components, we can compute these Hardy components by Cauchy integral formula, And this is the nonlinear analog of that. Okay, this is how you compute Riemann-Hilbert factors from a given function, but it's nonlinear, so it defined very abstractly. So I'm not going to go into the details.
So these are matrices now, right?
Yeah, things are now matrices. Yes, yeah. And this formulation depends on a factorization on the real line. Okay, so this is not a Riemann-Hilbert factorization. It's just a factorization on the real line, on the contour, and you get two weights. Okay, and once you get two weights, you can define. You can compute this Riemann-Hilbert factor. It's slightly technical, so unless somebody requests it, I won't define it. Okay, and then the main use of this formulation is to show that this nonlinear integration depends continuously on this data. Okay, so you can do some perturbation theory. So that's the main reason you would like to have some explicit formula. You want to be able to say, okay, if I perturb my data by epsilon, then I don't expect to see a lot of changes in my nonlinear integration. And that's
what can you tell us about these weights or reduction likely into that?
So I can tell. So usually we want this weight to be L2 and L infinity. Okay. So for instance, if you have this canonical factorization, right? If you have a look at this factorization, okay, this inverse here just convert that to plus. So and if you want to look, and the weight here just make everything 0 here. So one thing that we can observe here is that there's certain triangularity in the weight. Okay, but just a warning, this factorization is not going to work for our purpose because they lack a certain symmetry, and I will explain why we need certain symmetry. Okay, so these are the symmetry that we need in the weight. Okay, they can't be arbitrary. So this, I think, probably Dai, Vanakis, and Joe. Okay, these are extended the original method of Dai and Joe to the orthogonal polynomial setting. And they observed that they need to ensure these symmetries. Okay, so we want to have the phase in the positive weight to be increasing, and the phase in the negative weight to be decreasing. And why do we want to have that? Okay, so part of the Riemann-Hilbert problem, you have a function up here. You want to go down via a jump matrix. Okay, and you can deform the contour. And when you deform the contour because of a non-commutativity, this guy get moved up to the upper half plane, and this guy move up to the lower half plane. And when we deform the contour, we want to be sure that on the upper half plane there's some decay here. And we know, remember from the linear theory, if we want to have a decay in the upper half plane, you want the phase to be increasing. Okay, and if you want to have decay in the lower half plane, you want the phase to be decreasing. So this is exactly why you want to have those. Okay, so the deformation direction is guided by the local monotonicity of the phase, and these conditions appear very naturally in our stationary phase method. And I will. I think I have time, so I'll go into that. So let's just talk a little bit about Vazougin's localization principle. So what's localization? We have a function here, and these are stationary points, and we just modify the non-relevant bit. We localize it to small neighborhood of the stationary points.
So where's your function?
So these are scattering data array. So we just want to localize them to small neighborhood of stationary points.
So you have two curves there, right, or not?
Right. So the function is the big function here. You can define whichever you want, but the big function, and you want to bring it down to these very localized functions.
What is that doing? I'm sorry, I don't understand what that picture means.
So this is the original function, right?
Yeah.
And we would like to localize it to this function. As a consequence, we have to subtract it by this gray area.
So you want to localize near the stationary, yeah?
Yes.
Okay.
Yeah, you want to localize it, right? And you have to modify it by this some function h, and this oscillatory term just comes out because it gets multiplied by p and q. So you have to do that. So the main the essential idea and beautiful idea of Vazougin is let's decompose these oscillatory terms into two components using the Hardy decomposition, and let's handle it differently by different analysis. Okay, so So basically there's some decay estimate, okay. Some decay here, you have a lot of regularity, but the essential thing is you need the function h to be supported in the place where the phase is increasing, and has to be strictly inside, okay. That's what Vazukhin do. If you have the function h supported strictly inside the set where the phase is increasing, then you can get some decay estimate of this minus component, okay. So what I was able to do, I can do this very bad situation. We can allow the support of h to touch these endpoints, and you can have a sharp cutoff and so on. Okay, so and this is very important when you do phase reduction. When you do phase reduction and when you want to improve the regularity, you have to be able to do very sharp estimate. So let's just talk a little bit about how you can, why it is true from a heuristic level. Why is it true? Why do you get minus sign here? What's the relation to this positive sign? So if we think about the function h as supported in a very thin set near some point, then locally you can approximate this phase using Taylor's approximation. And this guy basically become a Fourier projection into this range. And here this actually become modulation. So you basically projecting into the frequency interval up to that point. And if this is positive, then as t equal to infinity, this frequency cutoff travels to minus infinity. And that's why you expect to have some decay. And once you believe that it decays, it's not too hard to use harmonic analysis to show it. To have some, if you have a regularity and a nice thing, you can prove decays. But we see there are two effects here. Okay, when t go to infinity, then this guy travels to infinity. But when alpha get close to the stationary point, it also negates the effect. So same story, you want to have some cutoff, okay, correct cutoff. And that's why I was able to handle these sharp cases. And it turns out to be, like I said, this thing turns out to be very important for the phase reduction, okay, when you have a very minimal changes in the function. And it's also important when you want to show that in the separation of the contribution, okay. So in linear theory, when you separate the contribution, it just separates the integral. It's easy, it's linear. But if you have a Riemann-Hilbert problem, it's not trivial. And these minimal decay are very useful to showing that certain orthogonality between these localized Riemann-Hilbert problems, and you can decouple them in the limit t equal to infinity. So it's really important, but I'm not going to go into the details. So I'll spend maybe 2 minutes talk about why. So we just talk about the localization principle, but we haven't talked about. I said like the phase monotonicity assumption arise naturally in our method, and I'm just going to explain it why. So for instance, if we like to modify the weight by some oscillatory function, okay, and this is Vazukhin's decomposition, okay, decompose it into Hardy components, and from his estimate, one of them will be small, okay, one of them will be small, okay, and small is good. We can always deal with it by Biot-Kaufmann formulation, okay. It depends continuously on the data, so we can always do something. And the large guy, and let's just assume that the phase is increasing, then we know that exactly this is the large component. So it has two properties. First of all, it has analytic continuation to the upper plane, okay. So if you have an increasing, then you have an analytic continuation to the upper plane. And it oscillates on the real line. Why does it oscillate? This function oscillates, and this is just some noise, right? So the h plus component here inherit the oscillation from the original function, and then okay. So how do we handle this term? We do it from using the Riemann-Hilbert structure. We don't do it using Biot-Kaufmann. We just modify this factorization by multiply it on the right by this I plus delta. Okay, so what does it do? So it does two things. First of all, this guy remains a Riemann-Hilbert factorization because I have a analytic continuation to the upper plane here. So it's still a Riemann-Hilbert factorization. Okay.
So where's the delta?
So I call it the remaining component. Okay, so if omega is increasing, then delta is this term. Okay. Okay, and I would like to modify my Riemann-Hilbert problem by the positive weight by this term, without affecting the nonlinear integration. Okay, and this small term you can do that because by continuity essentially, but for the large term you have to do something non-trivial, and I call it delta just for simplicity. So we multiply the Riemann-Hilbert factorization on the right. So it's still a Riemann-Hilbert factorization because delta has an analytic continuation to the upper half plane. Okay, it has and so on the other hand, the effect of multiplying on the right here is essentially adding to the positive weight because you have a triangularity. So when you multiply these two guys, essentially it's very small. You can treat it as a 0. So the effect of multiplying on the right here is essentially adding. Okay, so I can, that's why, so I achieve my effect of modifying the positive weight. But I would like to be sure that it doesn't affect my nonlinear integration. Okay, and if you look at the definition of the nonlinear integration, it's a lim of z m plus z, right? And we change m plus by some amount, so which is exactly this amount. Okay, and this m plus is normalized at infinity, so it's bounded. We don't care. What about z times delta z? And magically, delta z we can use Cauchy integral formula. So when we take the limit with z, it cancels out the bottom, and you get exactly the integration here. And this guy decays because delta oscillates on the real line. Okay, so it's designed exactly for this purpose. You have an analytic continuation to the upper half plane, and you have oscillation on the real line. So essentially, you see the increasing property here guarantees these two things. And that's why we need to have a increasing phases in omega plus. And you can do the same for omega minus. And at the end of the day, once you can guarantee those two symmetry, you can perform this localization and so on. I should stop. I can talk one more slide, but okay. So the canonical factorization here doesn't have that symmetry, and you have to do something. And that's why you see interaction of stationary points and the log term in the asymptotic. Okay, that's all. Thank you.